Centerville is the headquarters of Greedy Cablevision Incorporated. The cable company is about to expand service to two nearby towns, Springfield and Shelbyville. There needs to be cable connecting Centerville to both towns. The idea is to save on the cost of cable by arranging the cable in a Y-shaped configuration. Centerville is located at 9, 0 here on the coordinate plane. Springfield is at 0, 5 up here on the y-axis, and Shelbyville is at 0, -5 down here on the y-axis. The cable runs from Centerville to some point x, 0, which I've labeled here on the x-axis, where it splits into two branches going to Springfield and Shelbyville. Find the location that will minimize the amount of cable between the three towns and compute the amount of cable needed. So first, the configuration is going to look something like this, where the cable starts at Centerville, travels along the x-axis to the point x, 0, and then splits, and one branch goes to Springfield, the other branch goes to Shelbyville. Since we labeled the point where the cable splits x, 0, we know this horizontal distance here along the x-axis from the origin would have to be x units, which indicates the distance from Centerville to where the cable splits would have to be 9 minus x, this horizontal distance here. And now we need expressions for the distance the cable travels from where it splits to Shelbyville, as well as it splits to Springfield. Well, notice how we have right triangles, where we know this leg has a length of x, and this leg here in both right triangles has a length of 5. We're not using -5 here because we're thinking of this in terms of length. So now using the Pythagorean theorem, which is c squared equals a squared plus b squared, or c equals the square root of a squared plus b squared, where a and b the legs, the lengths from where the cable splits to the two towns can be labeled as the square root of x squared plus 5 squared, or x squared plus 25 in both cases. Again, this is due to the Pythagorean theorem. And now we have enough information to write a function to represent the distance the cable will travel, or the amount of cable needed. Let's go ahead and use the function d of x, where d of x equals, again starting at Centerville, the distance from Centerville to where the cable splits is 9 minus x, and then plus the two distances from where it splits to the two towns, which would be 2 times the square root of the quantity x squared plus 25. We want to minimize d of x, so now we determine the critical numbers, which is where the derivative is equal to 0 or undefined. But before we do this, of course, to find the derivative, we need to write the square root using the rational exponent of 1/2. We'll write d of x as d of x equals 9 minus x plus 2 times the quantity x squared plus 25 raised to the power of positive 1/2. And now let's determine d prime of x. The derivative of 9 is 0, minus the derivative of x, which is 1, giving us -1, and then plus, to differentiate 2 times the quantity x squared plus 25 to the power of 1/2, we need to apply the chain rule. We first multiply by 1/2. 2 times 1/2 is 1, and then we have times the quantity x squared plus 25, raised to the power of 1/2 minus 1, which is -1/2, and then times the derivative of the inner function of x squared plus 25, which is 2x. Let's go ahead and write this as -1 plus 2x divided by the square root of the quantity x squared plus 25. Notice by moving x squared plus 25 to the denominator, the exponent changed the signs, and I wrote the exponent of 1/2 as the square root. d prime of x is never undefined, and therefore to find the critical numbers, we set the derivative equal to 0 and solve for x. To solve this equation, let's first add 1 to both sides, which gives us 2x divided by the square root of the quantity x squared plus 25 equals 1. And now let's go ahead and multiply both sides of the equation by the square root of the quantity x squared plus 25. Simplifying, we have 2x equals the square root of the quantity x squared plus 25. Next, we will square both sides of the equation to undo the square root. This gives us 4x squared equals x squared plus 25. Subtract x squared on both sides gives us 3x squared equals 25. And we'll divide both sides by 3, giving us x squared equals 25 thirds. And now we'll take the square root of both sides of the equation. We do have two algebraic solutions, a positive and negative solution. But because you know x is a distance, we only need to use the positive critical number, which is x equals 5 divided by square root of 3. Notice the square root of 25 is 5. Again, we're not using the negative because we know x represents a distance, which has to be positive. Now for the next step, we need to verify whether d of x is minimized or maximized at x equals 5 divided by square root of 3. So we could analyze the graph of d of x, or we can apply the second derivative test by determining the second derivative and then verifying that if the critical number d of x is concave up, indicating we do have a minimum at x equals 5 divided by square root of 3. I did analyze the graph quickly, and it did verify that we do have a minimum at x equals 5 divided by square root of 3. But let's also apply the second derivative test. And to save some time, I've already written most of this out, where again we have d of x and then we have d prime of x. We need to find the derivative of the first derivative. The derivative of -1 is 0, and then to differentiate 2x times the quantity x squared plus 25 to the -1/2, we need to apply the product and the chain rule, where we have the first function 2x, and then to differentiate the second function, we multiply by -1/2, and then we have x squared plus 25 to the power of -1/2 minus 1, which gives us -3/2 as the power, and then times the derivative of x squared plus 25, which is 2x. And then we have plus the second function times the derivative of the first function. The derivative of 2x is equal to 2. Here I've already simplified the second derivative, and then next I evaluated the second derivative at 5 divided by square root of 3, and notice how it is positive or greater than 0, which indicates d of x is concave up at the critical number, and if it's concave up, we know that we have a relative minimum, or a minimum, at x equals 5 divided by square root of 3. So now that we've verified d of x is minimized at x equals 5 divided by square root of 3, we now know the location that will minimize the amount of cable between the three towns. And then to determine the amount of cable needed, we'll need to evaluate d of 5 divided by square root of 3. And again, to save some time, I've already done some of this work. We verify the critical number does minimize d of x, and therefore the location that minimizes the amount of cable is 5 divided by square root of 3, 0 on the x-axis, this point here. And then to find the amount of cable, we determine d of 5 divided by square root of 3, which again I've already set up and evaluated. The amount of cable needed is approximately 17.6603 units. I hope you found this helpful.